Hey guys, welcome to this video lecture series on the subject of polymer science and technology. I'm Harsh Panchal, Assistant Professor in Chemical Engineering Department of LJ Institute of Engineering and Technology. In previous video, we have understand the random degradation process. And we have also classified the degradation processes in the form of thermal degradation, photo-induced degradation, chemical degradation, and biological degradation. If you have missed that video, you can find it in the I button over here. Now, having said that, let's just focus on the thermal degradation. Right? We have seen that this thermal degradation is being influenced by the application of the heat. So when we apply heat on the chain polymer, this polymer start to degrade from its end point, or it can also be degraded in a random manner from any location of the long chain. Here, now we will discuss about the factor affecting this thermal degradation of the polymer. There are many factors and we will consider every factor one by one as we proceed in this course. The first one is the stability of the carbon-carbon bond between two monomers. Well, in order to understand this thing, I want to show you this three example of polyethylene, polypropylene and polybutane, right? So now let me just take a pen to explain this concept of this stability. You can see here that we have polyethylene structure like this. There is two carbon here like this. There is a chain of this carbon, but for the sake of the understanding, I am just only representing two carbon, right? There are n number of the carbon in this polyethylene, but I am representing only two carbon here. So both these carbon will have two hydrogen atom, one here, and this carbon will have one hydrogen, and here it will have one hydrogen, right? Now the structure of the polypropylene can be explained as, if I replace this specific hydrogen with CH3 group, it will become polypropylene like this. Here we have two carbon atom like this. This carbon is being attached with this hydrogen. Here we have one more hydrogen and here we have one more hydrogen, right? Now this specific hydrogen now been replaced with this CH3 group in order to have polypropylene. So here we have CH3 group, right? Now moving towards the third example, that is polyisobutane. It has a structure like this. We have two carbon one more time. This carbon has the one hydrogen here. This specific carbon has one more hydrogen. Now this carbon has two CH3 group like this. One more CH3 is being here. So you can see that this hydrogen is being now again replaced with this CH3. So now if you carefully look at these three examples, what outcome can be made by, or what statement we can make that this every molecule or every monomer is now becoming more bulky, right? You can see here this polyethylene is very much light molecule. And this polypropylene is relatively bulky group because it involves one CH3 group instead of the hydrogen. And this polyisobutane is now even more bulky, right? Because it has two CH3 group attached to its second carbon. Which means you can see here, as we move from left side to the right side, molecules become more and more bulky. So what statement we can make out of it? This, as your molecule become more and more bulky, your carbon and carbon bond becomes weak. So we can say that this polyethylene has highest carbon-carbon bond strength and polyisobutane has least strength of the carbon-carbon bond. So we can represent that this order of the strength of the carbon as the polyethylene has the highest carbon strength, it is being followed by the polypropylene, and the least carbon-carbon strength can be observed in the polyisobutane, right? So you can see here, as we move from left side to the right side, our molecule become more and more bulky. Hence your carbon and carbon bond strength which is decreased. And because of this decrement in your carbon-carbon strength, this particular polymer is now become less thermally stable. So here you can see that on the screen that now the bond, now the polymer which has the highest bulkiness is being thermally least stable, right? So your molecule or your polymer with the polyisobutane is the least stable or least thermally stable. Then polypropylene, which has only one CH3 group, is the intermediate when it's come to the thermal stability. And polyethylene is being highly thermally stable because it is having least CH3 group, or we can say it is not that much bulky in nature. So as bulkiness increases, it decreases your strength of the carbon-carbon bond, which ultimately directly affect on the thermal stability of the polymer. Now let's understand this thing with the one more example of three different groups, right? Now we will compare the stability of a different molecule with the standard of polyethylene. So again, let me just draw this polyethylene group as we have two carbon atom and hydrogen are being attached with this every carbon, right? Again, I am repeating that for the sake of understanding point of view, I am representing only two carbons. But in fact, this polyethylene has n number of such carbons. So it will have long chain of the polymer, right? Like this. But for the understanding point of view, I am representing only two molecules of every substance. Now, what is the polystyrene? Polystyrene is basically same kind of a compound, but instead of this hydrogen molecule, we will now have C6H5, right? We will now have C6H5, right? So you can see here that on the screen we have two carbon atom like this. Here we have two hydrogen. Here one hydrogen and one more hydrogen is being here. And we have one hydrogen here. But this specific hydrogen is now replaced with this C6H5 atom, right? So we have C6H5, and again it forms long chain of the polymer. So this is what we have as the polystyrene group. Now let's understand one more structure, that is polyalpha methyl styrene. So in this specific example, this hydrogen is now again being replaced with the methane group, that is nothing but CH3 group. So let's see what is the structure of this specific polymer is. You can see here we have two carbon atom, we have one hydrogen here and one more hydrogen is here. Now this hydrogen is now replaced with this CH3 group or methyl group, and at the down side we have C6 and H5. So this is the structure of the polyalpha methyl styrene. Now from the structure itself we can say that polyethylene is being more stable, while polystyrene and polyalpha methyl styrene are relatively less stable because they are much bulky. You can see here that this polystyrene has C6H5 group attached to the one of the carbon, which makes it even more bulky. And polyalpha methyl styrene has one CH3 above to the styrene, right? So it is even more and more bulkier than the styrene. So as we have already understood, as the bulkiness of your polymer increases, the carbon-carbon bond strength is being decreased. So as this strength decreases, which means your polymer is now more sensitive to the thermal effect. It means its thermal stability is being now reduced. So we can say that the least stability will be observed in this polyalpha methyl ethyl styrene. Then the polystyrene will have somewhat more stability than this compound, and ultimately polyethylene will have highest stability. So we can say that this polyethylene is being most stable compound or one of the most stable polymer, right? So here you can see that the dissociation of the carbon-carbon bond generate some amount of energy. if CH3 bond CH3 breaks, it will liberate around 88 kilocalorie per mole of the energy. So from these examples, we can say that as we keep adding different functional group or the substituent to the carbon chain, it will increase its bulkiness and it will reduce its thermal stability, right? As you can see here, this ethylene molecule or polyethylene has least substituent or least functional group, while polystyrene has one functional group as C6H5. And this polyalpha methylstyrene has a two functional group, or we can say two substance as CH3, two substituents as CH3 and C6H5. So its stability further reduces. But not always this is true, right? All the substituents do not always reduce the thermal stability of the polymeric system. Some of the examples are there which do not reduce the thermal stability of the polymer if their substituents are being continuous to added. Let me just take one example of this most used polymer of the Teflon. You can see here on the screen that the structure of the Teflon is relatively like this. And we have long chain of the polymer in this manner, right? So if we compare this thing with the ethane molecule, our polyethylene is like this. We have two carbon and four hydrogen in this manner attached to the each carbon, right? But this Teflon has a similar kind of a structure, but instead of this hydrogen, fluorine is replaced, right? So we have substitute as the fluorine. You can see here, every carbon is being attached with the fluorine group, that is F, in this way. One more F is there. Here one F, here one more F. Fluorine group is now attached with this every carbon, right? So all the substituent added to this carbon not reduce their thermal stability. You can see here on the screen that the example of Teflon has all the hydrogen atom is being replaced with the fluorine group. So its thermal stability should be less. But this Teflon is one of the most stable polymers. Despite being of having more substituent in the form of fluorine, this Teflon is one of the most stable polymer. So what is the unique property of this Teflon? You can see here that high negativity nature of the fluorine group protects your carbon-carbon bond from the Teflon. So whenever some external energy in the form of thermal energy, that is your heat or a light, strike to this carbon-carbon atom, the high negativity of the fluorine molecule protects your carbon-carbon bond to break out, right? So instead of this carbon-carbon bond, your fluorine group faces all the energies. And this is why this all molecule of the Teflon are being more thermally stable, because the fluorine group protect the carbon-carbon bond between the monomers. So this is the main reason why your Teflon is highly, or it is one of the most stable monomer or one of the most stable polymer. So now, having said that, this conclude the thermal stability, or we can say effect of the thermal stability on the polymer degradation process. There are several more effects that we will understand in an upcoming session. So with the examples, we have understand that as the bulkiness of the polymer increases, it reduces the carbon-carbon bond strength, which directly affects the stability, or we can say thermal stability of the polymer. But this is not always true. There are some type of the polymer which also has higher thermal stability in despite of having more substituent groups or more functional groups. Now we will see you in the next video. Till then, keep watching, keep learning. Thank you.